Hi, y'all. This is Dr. Houston. I hope you're doing well. So the first thing I want to ask is, did you all wash your hands like I told you to? Okay, maybe not the best thing in the world to joke about, but you know me. So what I want to do with this particular session is I want to take a look at some of the material that we've gone over already. This specifically is the start of chapter 18. This was basically the last half of class, the Friday before break, but not all of us were there, and it's also been a while since you guys have seen this, so I thought it might just be helpful to get this up for y'all. It also is helpful to me. It gives me a chance to practice a little bit with something that maybe we've seen already. So I'm going to share my screen with you here. I'm going to share, let's see, my PowerPoint. Hopefully this works. If not, I'm sure you guys will never see this video. So hopefully you're watching it right now with me. All right, so let's take a look. We've got here, it says we're chapter 18. What is this? Electric charges in motion. So we're going to be looking at things like electric current, and circuits, and we're going to be looking at resistors in series and parallel and capacitors in series and parallel. Sorry, there's trying to get myself situated here. All right. So first off, batteries. Well, you guys know about batteries. How do batteries move charges? Well, there's a chemical reaction that happens inside of there. Battery has a positive terminal and negative terminal. The batteries that we played with in lab were I think 1.2 volts. The battery that we see maybe right here, that's what a car battery looks like. That's typically a 12-volt battery. So moving forward, trying to move forward. Okay. If we've got charge moving through a wire, say, then the amount of charge that moves through that wire divided by the time it takes that charge to move is what's defined as the current. And a current is, the current is measured in amperes. An ampere is 1 coulomb per second. All right. So if the charges are always moving in the same direction, that's what we call direct current. This is the current that we would see from regular batteries, your double A's, your C's, your 9 volts. This is also what we would see with a car battery. Now, on the other hand, if we're plugged into a wall outlet, what we have is alternating current. And that's current that basically flips back and forth. It'll be moving in one direction and then the other, and one direction and the other. Well, you know, how is it that still works to run current through our circuits? Well, you guys saw that with a light bulb, it doesn't matter which way the light bulb was connected, which side was connected to positive and which side was connected to negative. As long as we had a complete circuit, we had current running through that light bulb. That's why, you know, our household lights work with alternating current. At least, yeah, our normal Edison style light bulbs do anyway. It gets a little more tricky when we start talking about LEDs. All right, so while I'm talking about alternating current, I want to mention that we can transform alternating current into direct current by using an AC-DC adapter. The little box that you guys plug into the wall that then you plug your cell phone into to charge is an AC-DC adapter. So your phone requires DC current in able to charge. Also, your laptop, when you plug into a wall, that little box that you're plugging in, well, there's a little box in the line somewhere that's an AC-DC adapter that converts the AC that you're getting out of the wall outlet to DC that actually will power your laptop. Moving forward. Okay, this problem talks about a pocket calculator. We've got a 3-volt battery that's powering this pocket calculator, and it's supplying a current of 0.17 milliamps. The question says that we leave this thing running for an hour and asks how much charge flows in the circuit, and also how much energy the battery delivers to the circuit over the course of this hour. So I'm going to now try to draw here, and we'll see how I do. Okay, there we go. There's a circuit. All right. We've got a battery over here on this side. It says 3 volts. Hopefully I'll get better with the drawing as we go on. I've just got a resistor here there to represent the circuitry of the pocket calculator. All right, so this says specifically that our current I is 0.17 milliamps. The book, by the way, uses a small I for current instead of a big I, but big I is more typical, so I'm going to use that here. Okay, so that's 1.7 times 10 to the negative 4 amps. The problem asks how much charge flows. Well, we know that current is charge. Let me see if I can clean this up just a little bit here. That's eraser, draw, charge is delta Q over delta T. Okay. So then my amount of charge that flows is going to be equal to current times time. And let's see, so my amount of charge is current, that's 1.7 times 10 to the negative 4 amps, times time, which is 1 hour. Now, of course, we don't operate in hours, we operate in seconds. That's 3,600 seconds. When I do the math there, that gives me 0.61 coulombs as my answer for part A. So this was part A. In part B, it asked about the amount of energy the battery delivers. Now, you guys may recall from chapter 17 that my change in electrical potential energy, which I have abbreviated EPE, your textbook uses capital U. But the change in electric potential energy, if I've got a charge moving through some potential difference, is equal to, well, the amount of charge that I have times the potential difference it moves through. So in the process of going around this circuit for an hour, this charge of 0.61 coulombs is being put through a total potential difference of 3 volts. That's the voltage on the battery. When I multiply these together, that gives me 1.8 joules as my amount of energy that's been used. All right, there we go. Let's see if this agrees with the next slide. Let's see if I can move to the next slide. Okay, what did I do? There and there. Oh, I guess I gotta erase all, clear all drawings. There we go. So yes, 0.61 coulombs and 1.8 joules. That's fantastic. I'll get there. I'll get there. Sorry. Okay. I'm just going to leave that spot there. Now, if we think about the charges that are actually moving, you guys know that you know, if I've got something like a wire, that the only way for charge to move is if it's the electrons that are moving. Protons can't move. Now, this is true in the solid state. If I've got maybe a solution and I've got ions, we can have positive and negative ions, and then I can have positive and negative moving charges. But typically, if I'm talking about circuitry, well, I'm talking about wires, that's solid, that's a solid material, and it's only the electrons that are flowing. So if we think about the direction of electron flow, it's exactly what you guys see in the drawing there, that my electrons are going to flow from the negative side of the battery, the shorter side in my schematic, towards the positive side. Now, unfortunately, due to a little history from Benjamin Franklin, we model our flowing current as if it's positive charges that are flowing rather than negative charges. So we'll typically use some kind of imaginary positive charges and visualize current that way. And that's the direction of conventional, what's called conventional current that you guys see right there. Okay. So how are voltage, current, and resistance related? Well, with Ohm's law. And Ohm's law says specifically that voltage is equal to current times resistance, or a potential difference is equal to current times resistance. I want to point out a couple things here. And that's specifically this circuit right here. We see some schematics. There's what my battery schematic looks like. There's a schematic for a resistor. And right here, we've got a switch. So we could open or close that switch to allow current to flow or to cut current off. The unit of resistance is the ohm, which is right there. It's represented with capital letter omega. All right, so what happens if we've got a flashlight that's powered with two 1.5 volt batteries? And it says that this flashlight provides 0.4 amps of current to my light bulb filament. And I'm supposed to determine the resistance of this filament. So the first thing I want to do is I want to try to draw here a schematic. There's one battery. There's another battery. Okay, and you notice how I've lined these two batteries up so that they're correctly oriented. So in other words, their positive sides are both facing the same direction. If they weren't, if the positive sides weren't both facing the same direction, and I'll try to draw in here, positive, negative, positive, negative. If my positive sides weren't both facing the same direction, then the batteries would basically be working against each other. It's what would happen if we had one of the batteries turned the wrong way? Well, we wouldn't expect the light bulb to light up, and it wouldn't, because we would be supplying the filament with 0 voltage. There's my light bulb filament. All right. Now, Ohm's law says that voltage is equal to current times resistance, or alternately, yeah, that's me again. Let's rearrange this. Resistance is equal to voltage over current. Well, I can use this to figure out the resistance of my light bulb filament. That's 3 volts total, because we've got 1.5 volts and 1.5 volts. That would give me 3 volts if I've got the batteries in correctly. Divided by 0.4 amps will give me an overall resistance of my light bulb filament of 7.5 ohms. So there's my answer for the question. Now, looking at this, this schematic here, right there, we've got a switch. Well, what's that switch? That's the on-off switch on the flashlight. Good, I agree with myself. And I think I just figured out something, how to work this a little better. So hopefully this will be a little smoother going forward. Probably not. All right, so here we've got a question. It says that we've got a circuit with a battery and a resistor. We've got some current flowing through that resistor I. It says the battery is removed and replaced with a different battery. And now apparently the current is 2I. Which of the following statements concerning the resistor is true? All right, at this point, I would like you to pause the video, think through things, and then play it. And this is the way we're going to handle these questions going forward. So I do want you guys to actively think about this rather than just listening to my answer. So I'm going to pause and now move on. But I depend on you guys to pause the video rather than me interjecting these artificial pauses and just having these things take more time. All right, the answer is that when the second battery is placed in the circuit, the resistance doesn't change. Well, the resistance, that's solely a function of the material that the resistor is made out of. So what do we do when we replace the battery? Apparently, we've supplied the circuit with a stronger battery. That's the only way that we're going to get an increased current through the circuit of 2I. We must have given it a battery that has twice the voltage because the resistor didn't change. All right. So how do we figure out the resistance of a material? Well, if we've got maybe, say, a material that looks like maybe a wire. We can picture a wire. A wire looks like a cylinder. And we think about the resistance of that wire. Well, the resistance of that wire is going to be dependent upon what the wire is made out of. All materials have a different response to current flow. Some of them, conductors, allow current to flow really well. Insulators obviously don't. And then, our different conductors, aluminum, copper, gold, silver, tungsten, have different amounts of resistivity. Some of them allow electrons to flow better than others. So the resistance of a wire is going to be dependent on the material, the length of the wire, and also the cross-sectional area of the wire. So if we've got a cylinder, then this cross-sectional area, what's that look like? Well, that looks like a circle. So if we picture the end of the cylinder, the end of the cylinder looks like a circle, and the area of the circle is pi r squared. All right. Here's some values of resistivities for different materials. You notice that all of our conductors here have very low resistivities. The insulators, on the other hand, have very high resistivities. All right. I want you to put yourself back in the lab, think about that first activity we did with a light bulb. We had a light bulb, we had a battery, and we had a wire. And I warned you guys not to connect the wire up to the battery by itself and kind of create a short circuit between the ends of the batteries, right? Well, I wanted to think about that and think about how much current actually flows through that wire if we do have a short circuit. So it says here that we've mistakenly connected the ends of our 1.2 volt battery to each other using a 24 AWG wire. AWG stands for American Wire Gauge. You don't need to know that, but you might see that at some point in the future. Yeah, not in this class, but maybe if you're having to worry about some electrician with your home or something like that. So it says specifically that this wire is aluminum and the wire is 5 centimeters long. We're asked how much current runs through the wire. All right, that's great. So what are we given here? We're given a voltage, 1.2 volts. We're asked for how much current's running through the wire. In order to figure that out, well, we could depend on Ohm's law. It says voltage is equal to current times resistance. But let's see, it looks like we don't have resistance yet, so we would need to figure out the resistance first. Resistance is equal to rho times L over A. Or this is what? Rho times L over pi r squared, if we think about a wire as a really long cylinder. Now we've got the length of the wire. We can look up the resistivity of aluminum. One thing we don't have is the radius of the wire. Well, let's see if we have any information about that. It says 24 AWG. 24 AWG means that the diameter of this wire is 0.51 millimeters. So if that's the case, then my radius of my wire is 0.252 millimeters. This is 2.52 times 10 to the negative 4 meters. And now I can go ahead and I can plug in some values. My resistivity for aluminum is 2.82 times 10 to the negative 8. The length of the wire, it says it's 5 centimeters. Of course, we're not going to operate in centimeters. We need to operate in meters. That's 5 times 10 to the negative 2 meters. And then on the bottom, we've got area. This is pi times my radius of my wire. And then we're squaring that. Okay. When we do that, we get actually a very low resistance. The resistance is 6.9 times 10 to the negative 3 ohms. So that's a little atypical. Well, I mean, it's typical of a wire, but usually if we're talking about resistances, we have values that are a lot higher than that for things like, I don't know, light bulb filaments and so on and so forth. Like the example we just saw, the resistance of a light bulb filament, 7.5 ohms. All right, so we were wanting to find the current. Current is voltage over resistance. In this case, our voltage is 1.2 volts. Our resistance is 6.9 times 10 to the negative 3 ohms. And as a result, we get out 174 amps of current. That is a lot of current. That would definitely be something to be concerned about. But the thing is, the battery is going to drain very, very quickly if we leave this disconnected. You know, we noticed that the wire got very hot. Let's see. This you know, could definitely burn us, but it turns out that the resistance of your body is quite a bit higher than this, and as a result, the current that the battery could drive through your body is quite a bit lower. So we don't really need to be concerned about handling batteries, which, you know, matches up with our day-to-day experience. Unless, of course, we start getting into higher voltage batteries, and then maybe we need to use a little more caution. And definitely don't go sticking any forks in any outlets. All right. This is going to end this one. I'll see if I can, whoops, that's not what I want to do. I want to go back. I want to, there we go. Oh, there's my face again. So hopefully this isn't too long. I will see you guys next time.